Hello, I'm Kaden Howell, and this is Continual Learning for Connectionist Networks. Consider a deep neural network, which was trained in roughly 2022 to map images of cars to their make and model. Now, a couple months pass, and the model's value plummets because, a 2023 BMW XM comes out, and the model was trained to be static. Now you have to retrain it on all of the data again, which is expensive in both cost and storage. But there are other considerations too. If you were in the medical field, the data might be more heavily constrained legally, and storing it might not even be an option, or if it is, it's a heavy burden to bear. Further, in the medical field, there's something called the Health Insurance Portability and Accountability Act, uh, and it puts heavy restrictions on being able to train a model in the cloud. Now, this is important because if you had a static model that you were trying to jointly train on all of your past data, that's going to be a lot of data. You're probably going to need to use some cloud environment for that. This is all to say that in the health space, and in other spaces, but also in the health space, having a dynamic model that could not have to rely on past inputs while still being able to have its representation updated would be a really good thing to have. Now, humans can do this very easily, and indeed our entire world is a dynamic world, so it's built for us. New words emerge all the time. New products emerge, our preferences for things change. The world through the human lens is a dynamic world, and humans have no problem adjusting to that. We can very quickly learn with very few amount of examples, but for DNNs, that's not necessarily the case. There is this concept called catastrophic forgetting that is the major roadblock to continual learning applications. In the 1980s, research scientists were trying to, I guess at that time they were just experimenting with their very early neural network models, and they kept coming across these like weird occurrences. Hinton was one such scientist who was finding these weird bugs, but essentially all of them just kind of ignored it and said it was easily avoidable until McCloskey and Cohen in 1989 actually decided to try and characterize what the problem was. And what they found was very fundamental to the architecture of the neural network. If you consider a 2-input, 1-output perceptron, right? In some kind of weight space, let's just say the weight space is this diagram on the right. We want to classify two different patterns. Say one pattern, 1, 1 maps to 1. The other pattern, 1, 0 maps to 0. That's all we care about right now. If you're joint training on both the patterns, then via back propagation, you consider each pattern perhaps in a batch, and you get carried right to the minimum space in the joint weight space, or the minimum loss area, which is that black region where the two shaded parts intersect. However, if you're only considering patterns for each one individually, and you train sequentially instead of jointly, you have this problem emerge where you enter one region and do well at that time on that task. But the second you move to train on the next task, you just leave the region. You have no regard. There is no incentive for the model to not take the easiest route to the next, to the best area in the weight space. And if that means leaving a place where the prior task had good performance, then so be it. Now, McCloskey and Cohen, they tried many different things to solve this problem. They tested different hidden sizes, tested different learning rates, tested freezing weights. They even tested orthogonal input representations, and they were pretty close with this one. If they had tried orthogonal hidden representations, they would have got more progress. That's actually a more valid strategy. But yeah, things didn't really work out for them. And then there's this fundamental idea that what's really going on here is related to what's called the stability plasticity dilemma. It's essentially that you can have it one of two ways. You can make your network and human brains, and this is a kind of connectionist in general thing. You can you can have it so that it's stable and doesn't absorb new information really well, or you can have it the other way around where it's plastic and new inform or old information gets overwritten very easily, but it's super good at absorbing new information. And the essentially the problem of continual learning on a large level boils down to trying to strike a good balance there to solve the catastrophic forgetting problem. So to formalize the continual learning objective, we can consider multiple tasks. Each task has data that comes from a different distribution. Um, the stream of data is typically said to be infinite, and the goal is one task after then another sequentially, each one having a different data distribution. We want to extend the model's knowledge. We don't want to overwrite anything. We want to keep extending it one by one. Now, in practice, we often make a simplifying assumption. We say that tasks come in sequentially in offline batches. Doing so is a good thing because it means that we can shuffle the batch and get IID assumptions. It also means that we can train for multiple epochs over the same batch. It's a much more difficult thing to do with an online assumption. Now, there's three subcategories of continual learning: the incremental task learning, incremental domain learning, and incremental class learning. Incremental task learning is what um, a majority, not a lot of the methods in the continual learning space for connectionist networks are in the incremental task setting. The idea is here is you have some shared layer and then some active head that's different for each task. It's called a multi-head system. And one thing to note here is that uh, for each head or for each example that comes in, we need some kind of task identifier to know which head to use. That's a distinction between incremental task learning and incremental domain and class learning. Incremental class learning is different in that we no longer consider it's now a single head system. And we also say that at some time t, you could have any class that has previously existed show up. Um, so really you're trying to, the labels at your class at time t are of the set of all labels thus far. In incremental domain learning, you actually say that the labels between the different tasks are the same. So in this case, you might have inputs that are from different distributions and are different values. Like, you have 0, 1, 2, 3, but you're trying to perform the same task on them. In this case, maybe binary classification of some kind of feature. So again, it's a single head model. And those are the three types that we deal with. Now, in the 1990s, I've already talked about it a little bit, but there are several early architectures. One such architecture is the activation sharpening. I I briefly said that if they had tried hidden distributed representations, they would have got somewhere. And this follows from activation sharpening, which is essentially taking the weight of or taking the activations on some nodes and then increasing it a little bit, but to offset that you decrease the other ones around you, and then essentially you create sparsity. uh, by creating sparsity and hopefully maintaining the same representation, um, you can move on to the next task, and the nodes in the network that don't have high activations because they're not being used for prior tasks can be used for the future task. Um, that's essentially that. Then you have replay. These are broad class of methods that exist well into today. And indeed, so do distributional representations, but I'll get to that later. Replay are um, let's see, the replay methods considered here are just a simple recency rehearsal, where the idea was simple. You take the three most recently trained items, add them to a buffer, and trade them with the newest item to prevent catastrophic forgetting. And then there's this sweep rehearsal, which is just every epic you randomly sample um, previously trained items to be in your memory buffer. And then there's this idea of pseudo rehearsal, which was developed in 1995. And at this stage, it was simply just you feed binary noise, a random binary vector into your model, you get an output, and then you simply want to keep the output, you want the outputs to stay the same when you feed that noise into your new trained model. So you can use that to kind of force the representation to stay in. There were also dual architectures based on this thing called the complementary learning system. This is another biological thing where it's believed the hippocampus quickly encodes new experiences. And then like the memories reactivated sometime maybe during sleep or recall. And then after being quickly encoded in the hippocampus, it's slowly and gradually integrated into the neocortex for more long-term storage. Um, yeah, it's essentially the stability plasticity dilemma. And scientists thought that they could uh, essentially emulate this with two separate networks that do the same thing. Now, in practice, these methods pretty much died out because they didn't produce very empirically strong results, but they were there. And then we also have dynamic node creation. A simple idea was to give more representational capacity to the network if it's running out. Um, this is also seen later. It's simple. If your error curve flattens out too early, then you expand the size of one of your hidden layers. Yeah, it was an early means of doing that. All right, so this is our taxonomy of continual learning. You can see there's a lot going on here, but we'll break it down one by one. So we're going to start with replay methods. We did just talk about an early replay method. In general, you got rehearsal and you have pseudo rehearsal, which follow the same rehearsal and pseudo rehearsals before, but with slightly, more modern design practices. Uh, the idea is that you can't store your entire past data set. That'd be impractical and violate privacy, and it's just not something you want to do. So instead, you can select a subset of the examples to store. The subset would be jointly trained with your new examples, and then hopefully the representation not only is strong for your new distribution, but contains elements of your old distribution. Um, Pseudo rehearsal, on the other hand, uses some kind of generative model, not just random binary noise anymore. We actually typically have a separate generator at this point, and we say that we want this generator to be trained on producing examples akin to the past distribution. And then that's what we feed into our model when we're training it on a new task. This completely gets rid of the necessity for some kind of memory bank, which is a very good thing. But on the minus side, you have to take care of this generative model, and these things can be a pain. They suffer from mode collapse, and you need to balance your examples really well. Otherwise, things can go wrong. Further, the rehearsal methods can be prone to overfitting the memory, and they won't theoretically do better than joint training ever, which is just kind of sad to know you're bounded like that. There's also this class called constrained methods. It's essentially replay where you have, or it's rehearsal, you have your old values. And what you want to do is consider all of those examples in your memory. You push them through your new network, and you want to take a gradient update that doesn't that doesn't work against any of the gradients for any of the examples, right? So we can look at it here. If the gradient of our new task is g, right, this would be almost directly in the opposite direction of a gradient created from a task one example. So instead, we choose a new gradient that is kind of the best of all worlds. It doesn't really hurt G and G1 anymore because they're orthogonal, but it does help G2. And this actually means we have backwards transfer. Uh, if G is helping, if G is moving in the direction of G2, you might expect that training on the new task also helps with training on the old task, or also helps with performance on the old task. So that's what you have here, but of course there's the additional problem of the extra computational complexity, but it's not too bad. Right, so now we can talk about regularization methods. These are broken down into prior and data focus. The prior focus methods essentially form some kind of posterior distribution over the parameters, and that distribution becomes the prior for your next task. Now, with this distribution over parameters, you can you can estimate things like the importance of certain parameters in your network, and by finding their importance, you can say, I'm going to not let my parameters that were important for prior tasks change too much, but the ones that were unimportant, they can change a lot. It's another way of tackling what should be stable and what should be plastic. Now, if we look at elastic weight consolidation, it's a perfect example of this, and it has this nice physical intuition behind it, whereby you can think of the gray low area space, the gray low error space. Clearly, the minor axis moving along that would cause a change in error more quickly than moving along the major axis. So you can think of it as there being a stiffer spring on theta A stars that are aligned with or want to move in the minor axis compared to those which want to take updates in the major axis direction. So by taking this update, we can see that it's constrained back. The update is constrained back into this low region error for both tasks. Again, the real downside to this is that you need to store additional information. It varies method to method, but you need to store some kind of information for each parameter to say how important it is. Now, data focus methods follow from Hinton's 2014 work on knowledge distillation. The idea is simple. If you take a example, or actually, let me back up. The idea is simple. If you want to classify a BMW, you would expect that a garbage truck has a higher misclassification probability than a carrot does. The essence being there is valuable information encoded in those output probabilities, and we want to use that output probability to help force old representations into our new task. We do this by sending an example for our new task into the old model, seeing what its output distribution is, and then comparing that to what we want what the output distribution is when we send that same example into our new model. Now, this is nice because like the other regularization method, there's no memory needed, and it can be, it's often used with other methods like iCarl, which is a rehearsal method. But then there's this problem where after a time t, the old task knowledge is integrated to a new task model, right? But then you go to time t plus 1, and that old model starts trying to push its knowledge into the new model. And you get this kind of lossy compression that happens over and over and over again. The error compounds, and you start to get just a bad result. And indeed, like you might even start seeing domain shift between or to your new tasks because the representations from your old tasks are kind of out of whack and they don't really mean much anymore. So then we also have parameter isolation methods. Um, these can be fixed and dynamic. In fixed parameter isolation methods, the idea is simple. We have a constrained neural network with there's not a lot to change in size, and we want to force as much representation into it as possible across a number of tasks. Now, of course, that means that you have to choose an initial network size that's smart, like a good initial network size. But let's look at an example real quick. We have PACnet here, which in practice performs very well on a bunch of continual learning tasks. Um, Consider it training, right? We train it, we prune away everything with a low activation. We do some retraining to solidify those weights, freeze them, and then the process repeats for the next task. By doing this, we're essentially forcing representational capacity or we're forcing representation into the network. There's also another note with this PACnet method. It's that the tasks at some time can use the weights of the prior tasks. They just can't modify them at all. So yeah, again, there's no episodic memory needed, and this method might sound very similar to the activation sharpening method of before. You're essentially trying to create orthogonal representations, and indeed you do here because you're, isolating parameters to certain nodes, or it's largely orthogonal. Um, the other thing is you need a task oracle when you're doing this method. You need to know what parameters you actually are frozen into. So when you go to do inference, you need to say, hey, I need these parameters to help me classify something in task 5 or whatever it is. Also, there's this catastrophic problem where the network fills, you miss a portion memory, the network's full, you're kind of out of luck. Because the weights are frozen for previous time steps. And if the network's as full as it's going to get, that's just how it is. Um, and then, yeah, for certain parameter isolation methods, backwards transfer is not possible, but for other ones, it still is. Now we have dynamic parameter isolation, and this is kind of the flip side of the coin. Instead of saying we have fixed weight we want to compact representation into, we say we have a network, and this network can expand as needed, kind of like dynamic node creation in the 90s, but with more steps. So again, there's not really a memory needed in this case. And then also we have the fact that backwards transfer is possible, which is a good thing. Specifically if two tasks are related, it's often found that, learning one should help the other. And in this case, it is. Many of the methods don't actually need a task oracle in this case. And then networks can grow, as I said, as much as they need. Now, here's the big problem with this. It's if you miss, you got to set your hyperparameters correctly. You got to set your thresholds for when to grow. If you mess up, you're going to either grow too big or remain too small. You got to strike that balance, and that can, in practice, be a somewhat hard thing to do. So you need to watch out for that. Oh, and further for those dynamic methods, your complexity can grow quite large if you just keep adding on tasks. Now we can go ahead and consider some of the data sets that are used to actually quantify uh, how good continual learning is. One of the common ones is called permuted MNIST. You essentially take MNIST and you apply a constant permutation to all the classes. And what you want is for uh, the new permutation, say that's a new task, you want it to be able to learn to classify on that permutation, but also be able to classify for old permutations. Now, The feature representations in this case are considered to be pretty similar, but in practice, you can go to much more complicated sets, and things start to fall apart. And that's actually found with a lot of these methods is that they work well and they're very, perfect little research home, but then you take them to the real world and they fall apart. So there's FearNet, which is something I haven't introduced in this paper, but for the purposes here, they they did a study and they used more complicated data sets to try and quantify which models were doing well, and they considered data permutations, they considered incremental class learning, and they considered multimodal learning. Um, they considered, or they used the Cub 200. It's just like 200 different species of birds, and they also used audio set, which is YouTube videos with 10-second sound clips from 632 classes and over 200 or 2 million annotations, right? What they found will be presented in the next section. So let me just quickly talk about Core 50 real quick. That's a data set that's composed of 50 classes of objects. These objects are observed, from different perspectives. You got different backgrounds, illuminations, blurrings, occlusions, poses, and scales for like all of the different objects. Um, and the examples that are in this data set were collected such that they look like they were taken from a robot's point of view. Whatever that means, it means that uh, this data set was more designed for, robotic systems. Um, yeah, so let's move on here. The empirical findings, this was all done by a 2022 study pretty much. This is also some of the findings from the FearNet study, but largely one of the most recent and most complete studies that have come out of continual learning came out kind of recently by Delange or Delange. Um, and what they found was that, as I said before, PACnet performs pretty well over everything, but nothing yet can quite beat joint training, which is upsetting. Some methods that were, developed for the class incremental setting actually still do pretty well in the task incremental setting. Um, Prior focus methods will do well if tasks are similar. Consider like um, the what's it called, the permutation methods of like MNIST, right? Those are pretty similar data distributions, so that's where prior focus methods might do well. Data focused methods, on the other hand, have problems with large distribution shifts. So in the multimodal setting, they don't do that well. Um, and then it was also found that task order doesn't really have that much of effect on the classification of everything. Now, as I said, most of this work came from 2022, but an earlier study, earlier survey by Parisi, basically had him quoted saying like, there is no established consensus on benchmark data sets and metrics for their proper evaluation. Essentially, there's two methods are too highly heterogeneous and limited, and there's limited evaluation schemes to assess the performance. Essentially, what he's saying is that methods all have their little quirks, and testing them under the same microscope is, in practice, a difficult thing to do, and it hasn't really been done well. Even the survey in 2022, where most of these results are taken from, only really considers the task incremental setting as a simplifying assumption. All right, so future work. The problem with continual learning right now is that it's a closed world problem. Now, a survey from 2023 by Munt uh, argued that the continual learning problem it's too narrow. It's right now it's not what it should be. Uh, Really, it should be a superset, and it should encompass a different domain of problem called active learning. And what is active learning? If continual learning asks, given some incremental data, how do we choose the best model, or how do we update the best model? Active learning kind of asks the flip coin question, where it's like given some model, you know, what's the best data we can query for it? Now, active learning more specifically assumes that it has a bunch of unlabeled data to query from, and it wants to choose some subset of the data to push over to humans or experts to label, which would then be given to the model. And it wants to choose that subset to maximize performance. The motivation there is largely that data acquisition is inexpensive, especially when compared to data labeling, especially when in the hands of experts. So the problem is that's also a closed world task. And primarily what that means is that each of these tasks do not operate well if there's out of distribution data. So data can be categorized into knowns, known unknowns, and unknown unknowns, right? Your knowns are the things your model gets all the time. It's good at them. It classifies them well. And likewise, your known unknowns, maybe they're harder to classify. Maybe there's fewer examples, but your model knows what they are and knows that it can't be as confident in their classification. But then there's also unknown unknowns, which are just out of distribution, and your model might overconfidently misclassify them. The question is, how do we make these two closed world tasks safe from unknown data? The answer is we add in a third problem called open set recognition. And just as I described, the entire existence of this this type of problem solution is to determine what has and hasn't been seen yet, and maybe even set aside unseen things for later so that they can be trained on. But now if we add this in, we have protections, right? We have protections for the model, and we have protections for the active learning. So from this perspective, you can imagine an incoming stream of data, right? Constantly incoming. You select a way, you remove the things that haven't been seen, and maybe the open set recognition goes to the active learner and says, hey, I have all of this new data for you. Pick out a subset that we should label and give to the continual learner. It does so, it returns it to the open set recognition, who passes it back over all clean and free of the noise of unknown data. And continual learning can then more robustly update its model with better data. That's the paradigm Munt wants to see happen, and I completely agree. This is where the field of continual learning should be headed. Continual learning, you should be able to draw a circle around all three of these circles and call that continual learning. That's where we should be at. And then on a more personal note, the one thing I would like to see more of is a relaxation of the offline batch assumption. It really happens in much, like the majority of the literature. And I don't necessarily agree that that's how data would always come in the real world. I think data should be able to come in arbitrarily. Task boundaries shouldn't need to be, extremely divisible. They should be able to be vague, and classes should be able to exist across maybe different tasks even. There should be some kind of organizational structure to sort that out and then respond as necessary. Anyway, yeah, continual learning very quickly. Thank you guys for watching. Take care.